Okay, we are looking at problem number 19 from section 2.2. In this problem, we have a silver dollar is dropped from the top of a building that is 1,361 feet tall. Use the position function below for free falling objects. The position function is S of t equals negative 16t squared plus v naught t plus s naught. And for part A, we're asked to determine the position and velocity functions for the coin. So in this situation, we have a building and we have a coin that, we can assume that it's just dropped from the top of the building. So its initial velocity, you can think of it as its initial speed. It's not moving before it's dropped. And its initial height is just going to be equal to the height of the building. Those are kind of some assumptions that they expect us to make. You probably could imagine that person isn't dropping it from, like right at the top of the building, but imagine they're just hanging over the edge dropping it. So for the position function, while we are given the position function, there's a couple components that are missing. We're missing the initial velocity. So that v naught, the subscript of 0, that means the initial. It's a specific value of v. So it's the function v evaluated for when t equals 0. It's that initial. And same with the subscript on the s naught. That subscript of 0 means the initial. So subscript of 0 is common notation to say an initial value or initial point, or the value when the normal indice, so in this case the t equals 0. So what we have is that the initial velocity, it's not moving. So its initial velocity is just going to be 0. It starts off before it's dropped, it's not moving at all, and then it starts to drop, and it, is going to increase speed based on the acceleration of gravity. And that's where you have that negative 16t squared that actually deals with that comes from the acceleration of gravity, and the acceleration of gravity in terms of the English system of measurements is going to be 32 feet per second. So that's where they get that negative 16t. You'll probably see that a little bit later on as you progress through calculus. And then our initial height, again, we're just going to assume that's the height of the building based on the context of the problem. So then filling in the blanks, we have this negative 16t squared plus 0t plus 1,361. We really don't need that 0t term. So we can just say that this is negative 16t squared plus 1,361. And then for v of t, the velocity is given by the derivative of the position function. So here, if I take s prime of t, that's equivalent to the velocity function. So s prime of t, now that we have that, we apply the power rule to that first term, giving us a negative 32t. And again, that comes from the acceleration of gravity. That coefficient, the acceleration of gravity, is at negative 32 feet per second. If you encounter a problem like this where it's using the metric system of measurements, you're going to have a 9.8, or you might have it with 10 or something like that. And then the derivative of a constant is just going to be 0. So for our v prime of t, we have negative 32t for our velocity function. And then it wants us to determine the average velocity on the interval. So we just want to take the rate of change of v with respect to the rate of change of time. So to do this problem, we need to know what is v, since we're going from t equals 1 to t equals 2, what is v when t equals 1? In this case, that's going to be a negative 32. And then we also want to know what is v when t equals 2. So plugging that into the function, we get a negative 64. So my change in v is going to be negative 64 minus a negative 32 over my change in t, time, which is going to be a 2 minus 1. So the negative 64 minus a negative 32, that's going to give me a negative 32. And then my change in time is going to be 1. So our average velocity on this interval is a negative 32. You don't have to put that 1 in the denominator. Find the instantaneous velocities when t equals 1 second and t equals 2 seconds. So we've actually already done that. We've looked at finding v of 1 and finding v of 2. So we can just plug in those values. This is going to be a negative 32, and this is going to be a negative 64. And part of the object accelerating and gravity causing the object to accelerate, you're going to expect to see the velocity to increase. Because if it's positively accelerating, that means that the change in velocity is going up. It's not a constant velocity. It's increasing. So we should see a change in that velocity as time goes on until it hits the ground. Find the time required for the coin to reach ground level. Okay, so to reach ground level, we're really looking at the position of the silver dollar to be 0. You know, we started off with 1,361 feet above ground. So when we hit the ground, that's going to be where our height is 0. So we want to, go ahead and we have this position function. And so we want to know for our position function, we have s of t equals negative 16t squared plus 1,361. And we want to know when does that equal 0. So for what value of t does this equal 0? So we end up with solving a quadratic equation. And this one doesn't have a t to the first. There's no coefficient for t to the first. So you could solve it, you know, very quickly, maybe divide both sides by 16. At this point, I'm going to pull out a calculator just for algorithmic purposes. You could also use the quadratic formula. So right now it's not looking like it's going to be a nice answer, but we have this negative t squared. When I divide both sides by this negative 16t, we end up with plus 85.0625. And again, I'm not considering significant digits, so you might want to pay attention to that. So we get t squared. When we add t squared to both sides equals 85.0625. And from there, we just want to take the square root of both sides. Of course, we do end up with two values for, or two possible values for our t. However, we're not going to consider the negative because we don't have negative time since we're dealing with a finite value of time, or just so then this gives us the absolute value of t equals, if I'm just rounding it, 2.2.3. And again, I'm not paying attention to significant bit gears. So round to 3 decimal places. So we are going to look at 9.2.2.3 seconds. Find the velocity of the coin at impact. So we know the time it takes to impact the ground. What's the velocity at that part? We can just look at evaluating v of 9.2.23. In other words, negative 32 times that 9.2.23. And when we evaluate that, we get this 295.136. When we round it out to 3 decimal places, if you use the calculator value for the t in part D, you might get a slightly different answer. Okay, and that concludes this problem. Thank you.